nearly 50 have joined this meet. I know that scores of candidates are following this meet through YouTube. I welcome all of you, and our department is proudly organizing this 1 week faculty development program. So this will be very useful to all the participants during this pandemic holidays. It's a rare opportunity. So I ask all of you to make this program to the maximum benefit, because the resource persons will be giving you many valid points. So I ask all participants to take your pen and notebook so that you can note the important points. The resource persons will be giving you some new definitions, open problems, conjectures, paradoxes, and whatnot. So this will be very useful to you, whether you are a research scholar or a research guide. So all of you make this program a success, and you participate in this program with full enthusiasm. So I ask all participants to actively participate in this program. I think at the end of this program, the organizing secretary, Dr. Jackson, will be giving you some time during which you can raise your doubts, and the resource persons will be clarifying your doubts. So I ask the participants again not to go in the middle. You stay tuned to this meet till the end. That is till the vote of thanks is proposed. I once again welcome all of you to this week-long faculty development program. Thank you.
Thank you, sir, for the welcome address. May I now request our beloved and respected Principal, Dr. C. Veerabaku, to deliver the inaugural address. Sir, would you please?
Good morning, everybody. Respected resource persons, Dr. Kala ma'am from MS University, respected head of the department, Dr. Nagarajan from our Vivo Chidambaram College, revered professors from the VOC College and other colleges, my dear research scholars and PG students, all of you, I'm very happy to see all of you through this Zoom meeting today. As a principal of this great institution, I wholeheartedly congratulate my math department people, because they have arranged a wonderful seminar through Zoom. I think maybe, if my remembrance is right, this is a 5-day program. We have been doing a lot of activities from the first lockdown onwards. Today, it has been continuing through the math department of our VO Chidambaram College. Maybe most of the things we have shared through the WhatsApp, FB, Insta, Twitter, and Twitter also. So it's my request, Jack, all of them, if they mute, it would be easy for them to convey my message to all. So I request the participants, if they mute, it would be easy for them to convey my message to them very clearly.
Sir, unmute yourself. Sir, I have muted all. Kindly unmute yourself, sir.
Is it here?
Yes, sir. Yes, sir. Yes, sir.
Shall we start, Jack?
Definitely, sir. Definitely, sir. Please.
Previously, what I said, is it audible or not?
Yes, sir. You are audible, sir.
Now it's audible. Before that, what I speak, whether have you reached or not?
Reached, sir. Reached. I have muted all other participants, sir. Please.
Okay. Vivo Chidambaram College is a standing monument which carries forever the name and fame of that great patriot, legal luminary, Sudeshi's team navigator, and above all, a humane person of this area. This college was founded by Kulabadi APC Veerabahu, who has dedicated his life, energy, and wealth for the building of this college into a premier institute of higher learning, especially in the south skits of Tamil Nadu. As a principal of this great institution, 7 decades has gone. So far, at present, we are having 3,000 students in the regular stream as well as the unaided stream. And we are having 122 staff members that is to make the cut. 10 departments have been elevated as a research center by our university. Whether you believe it or not, in my part as a principal, I am very proud to say that more than 177 research colleges are pursuing their research program under the able guidance of our faculty members, which includes both science as well as humanities. We have retained A grade in NAC consecutively in the year 2004, 11 and 17 respectively. In addition to that, we have got a NIRF ranking also. If I want to tell, 2 times we got a NIRF rank. In the year 2019, we got 77th, but in the year 2020, we got a 68th position all over the India. In addition to that, as far as the Vivo Chidambaram College is concerned, it strives to make significant, sustainable, and social responsible contribution to the society. It also serves a center of knowledge by providing the highest quality of research-led teaching. The college actively promotes research and inculcate research culture in enriching and enhancing the professional competence and competence of faculty and students. Riding high, our institution has introduced a wide range of consultancy services, especially in the chemistry as well as the geology department. In addition to that, in our part to make the cut, which I have already told that 10 departments have been elevated as a research center, to be on the up and up, the Vivo Chidambaram College, from its inception, has made roads into getting various seminars, workshops, projects to the tune of 7.54 crores from funding agencies like UGC, DST, DBT, CSAR, and other government funding agencies. We have been tapping grants from the UGC for the development of UG department as well as the PG departments. As you all know, there's today's scenario of the educational institutions, which includes universities and colleges. Without the grant, we cannot dream about for the development of the institution. So far, the Vivo Chidambaram College achievements as a principal, this is the time to thank my yesteryear professors, ex-principals, and the present professors, those who are all working actively not only in an active manner, they are my professors. I'm very fortunate to be the principal of this great institution. The legacy continues because of the teamwork. So whatever the management as a principal, if I request my faculty members, they are having an unstinting support for the development of this institution. So this is the teamwork which I am very happy to share to all my colleagues and all other college professors also. A principal of an individual person cannot do anything for the development of an educational institution. So it's a teamwork. I have been proudly say that from the first lockdown onwards, so far we have been conducting more than 75 to 85 webinars. In addition to that, our professors came forward and developed some videos also for the awareness of the public due to this COVID-19 pandemic situation. So we have been actively involving for that social responsible scheme also. We have signed several MOUs with educational institutions. Recently, we have signed MOU with the Fisheries College Research Institution. It has been that is Dr. Jayalalitha University, affiliated by the Dr. Jayalalitha Veterinary Research University, and we have signed Multilinguistic Center MOU, and we have signed one MOU for the welfare of the students community. We have been associating with the Bharatidasan University for the introduction of the IECD program. For the betterment of the students, our faculty members have been doing a lot of activities, especially the academic activities we have been doing. This is the one example. Actually, more than 500 people are seeing in this webinar through the development of the Vivo Chidambaram College, what development have been made by us, not me, made by us. So this is the entire credit goes to my faculty members because of their support, because of their dedication, because of their devotion only. The Vivo Chidambaram College would have come up and reached in this level now. As just few minutes back, I told you that this is the time to thank my yesterday professors and pharma principals, the management, especially the founder secretary, Kulabadi APC Veerabahu, and the present secretary, the most respected personality, 3 APCV Chokalingam, have been continuing the secretary since 1982 for his valuable, remarkable achievements. We have been slowly getting through what we are having as far as the resources is concerned. We have been developing for the development of the society through our educational institution. In addition to that, in our part, as you all know, you are all faculty members, you are all professors, you are all PG students, you are all research scholars. Nowadays, the education is being commercialized. But we, the VOCN, on stand, we very proud to say that our founder secretary principle is that on any account, the educational should not be commercialized. Even though we are facing so much of financial constraints, we, the management, we have been sticking on the same principle on any account as a principle. I can give an assurance through this webinar, on any account, we will not sell the education, because education is very important for the development of the society. So our founder dreams has come and true. So in addition to that, not only that academic side, in addition to that, as a principal, we have been tapping a grants from UGC. We have constructed multi-purpose gymnasium, indoor stadium for the students' sports activities. We have been developing that synthetic tennis court also. Our professors have been publishing a lot of research paper in the national and the international level. And now the math department, each and every department of our college, it's having its own unique. If I want to point out regarding that math department of our college, they have created one endowment in the name of Dr. Professor S.S. Pillai. Whether you believe it or not, they have been doing a wonderful job through this S.S. Pillai endowment. And every year they have been conducting a quiz program for the school students. And the math department is also publishing a e-math letter also. In my period, I have requested all my professors, especially the heads of the department of our college, which includes science and humanities, they have been developing a blog also. Very soon you can also see our department profile. So we have been developing a maximum with the help of this educational institution to the students community. In this time, I would like to say only one point. Our founder principal, our founder secretary Kulabadi APC Veerabahu, he has given a one word to the incumbent secretary to Mr. APCB Chokkalingam. First thing which I have already told you, that on any account the education should not be commercialized. We are keeping on his principle. In addition to that, he said very clearly to our present secretary, I have founded this educational institution only for the downtrodden people in and around Thoothukudi. So, as you all know, most of the students hailing from the poor economic background, not only that, highly meritorious also, but because of poor economic background, they are not in a position to continue their higher studies. But VOC, we have been doing a real service to the society for giving a opportunity for the poor economic people, and in addition to that, economically downtrodden students also. Most of the personalities, they have been successfully completed their education through this educational institution. Now they are occupying a well position, and this legacy continues forever. As I told my colleagues always, men may come and go, but the educational institution is present always. Because as my secretary, he told me that whatever you do, you have to take it in a right spirit with a service mind. With the blessings of our founder secretary and present secretary, 3APCB Chokkalingam, not only me, our team, I mean the Vivo Chidambaram College people, we have been doing a real service to the society through our educational institution. With this word, I conclude my speech. I wholeheartedly welcome once again to all our resource persons, research scholars and PG students. And really, once again, I thank from the bottom of my heart to the math department of our college, especially Dr. Nagarajan, head of the department, and his colleagues. Thank you one and all. Bye. Over to Jackson.
Thank you, sir, for elucidating the pride of our college and being the driving force of every program happening in our college. Thank you once again. May I now invite our HOD, Dr. A. Nagarajan, Associate Professor of the PG and Research Department of Mathematics, VO Chidambaram College, coordinator of this faculty development program, to introduce the respected chief guest, resource person, Dr. R. Kala. Sir, please.
Okay. She is having a long profile, but I will short it into a smaller one. First, she secured third rank in BSc and 8th rank in MSc and second rank in MPhil in MKU, because before 1990 it is Madurai Kamaraj University. In Madurai Kamaraj University she secured these ranks and also obtained her PhD in MS University under the guidance of Dr. S. Arumugam, and now joined as a lecturer in Parasakti College in 1996, worked up to 2000, and then joined MS University Department of Mathematics. Till now she is working there, and now she is a head and professor of mathematics. Her total teaching experience is 23 years and her research experience is 29 years. 27 scholars obtained PhD and 10 scholars pursuing PhD under her. She published 127 research papers in national and international level and also published 3 books for credit. She completed 2 DSc projects, and she has also attended more than 100 conferences and acted as a resource person for more than 60 conferences. With this introduction, moreover, she is a very calm nature and kind enough. Whenever we approach the department, she will always give her help regarding academic as well as research purpose, and also sincere in his work and perfect and sincere in his work. I know him. I think in 1991-90. I think I met her in research department of mathematics in Palayam Kotai, and where she has joined in as a research scholar. From there itself, I know her very well. She is a very good personality and always helping everyone who approaches her, and such a nice person. And first time we invite you to give a lecture to our department, madam. I wholeheartedly welcome you for our department. Thank you. Now I hand over this to Dr. Safina, madam. Thank you.
Thank you, sir. On behalf of everyone here, I now invite our respected chief guest, resource person Dr. R. Kala, Professor and Head of the Maths Department, Manonmaniam Sundarnad University, to enlighten us on the topic of semigraphs with her talk. Please, ma'am.
So, good morning, everyone. So, respected Secretary of VOC College, respected Principal of VOC College, respected Head of the Department, other faculty members, and all the participants who have joined this webinar in this virtual mode. So, good morning to each and every one of you. So, at the outset, let me congratulate this VOC College, the Department of Mathematics, for organizing this, and also I thank them for giving me this opportunity. So, as aptly said by the principal, hands off to their principal, to their principle, that is non-commercializing education. So, very few colleges out there. So, thank you, sir. So, thank you for sticking on to that principle. And also, as far as this mathematics department is concerned, they have a very great asset. That is the work of Dr. Sivashankara Narayana Pillai in his own handwriting that is preserved in their library. It is a very great asset. Any college can always can boast. Okay. So with these few words, once again, I thank the Department of Mathematics for giving me this opportunity. And let me go to my topic, that is Introduction to Semigraphs. Okay. So let me start sharing the screen. So thank you, Principal Sir. Thank you for being.
Thank you, ma'am. Thank you, ma'am. Ma'am, I'm having some other work. Please, ma'am, permit me.
Sure, sir. Sure.
Thank you, ma'am.
Thank you, sir. Thank you. So can you see the screen?
Yes, ma'am.
Okay. So I would dedicate my talk to this legend. He is Professor Sambat Kumar, a legend in graph theory. And the semi-graphs that is introduced by him. See, he is the first one to teach graph theory in India in the year 1967. So he taught this graph theory to his students in a PG course that is in Mysore University. And one of his students is Professor Acharya, who is again a legend in graph theory. So these two persons, along with so many in southern part, that is Professor Arumugham, Professor Tamil Chelvam, and then Professor Swaminathan sir, all of them, they contributed to the promotion of graph theory in this South India. So this person, when he taught graph theory as a course in the year 1967, he felt that vertices enjoy more properties than edges. That is what he felt. And why this difference? Why not both of them enjoy the same properties or same privileges? That was a thought running through his mind always. So once he has gone to his friend's house, and as many of us have in our houses, he could see this beads, this string, the two ends tied to the two corners of the door with string of beads. First of all, it is descending and then ascending. So you have uniformity there. And it looks the same whether you look at from the left or from the right. Okay. So this gave this look of this beads. It suggested him a definition, and that is what he defined as graphoidal covers first. And as you want to know, this graphoidal cover is the base for PhD thesis of Professor C. Patyam of UOC College. A full complete PhD thesis was done on this graphoidal covers. And the motivation is this very simple thing, that is this bead, string of beads. And Professor Sampat Kumar, he defined initially as graphoidal covers, and later Professor Acharya, he renamed this as semigraphs. So before entering into the formal definition, I wanted to give a base on this. And you can see that the importance of the semigraph is here vertices enjoy equal properties as edges. Okay. For example, if you look at a graph, if you take the star,
ma'am,
star,
pardon me, ma'am.
Yes.
Are you presenting some screen with pictures or anything we're not able to see?
No, I am showing a bead. It is not visible for you.
We don't see a presentation.
Have you pinned me, ma'am? Have you pinned by me?
Yes.
Yes, ma'am.
Yes.
Kala MSU.
Yes, ma'am.
Jackson, is it not visible, the screen?
Ma'am, now only we just see your screen, ma'am, but not your presentation.
No, that string of beads that is not seen?
No, ma'am.
We can see your Google Meet screen, ma'am, nothing else.
Oh. Then I'll share again.
Okay, ma'am. Thank you.
Can you see the picture of Professor Sampat Kumar?
Yes, ma'am. Now it's visible, ma'am.
Now we can see it. Yes.
Okay.
Thank you, ma'am.
So this is the first thing I started with. Okay. So now is the string visible?
Yes, ma'am. Yes, it's visible,
yes.
ma'am.
Okay. So this diagram is the motivation for the definition of semigraphs. Okay. And you can see that when you look at this K1, n, what you call as the star graph, there you have a single vertex and you have all those pendant vertices. They are mutually non-adjacent, but all of them adjacent to the same vertex. Okay, that is a property of a vertex. But you cannot have that property for an edge. You can have only two non-adjacent edges adjacent to or common edge. Okay. But here in the semi-graph, each one is taken as an edge. You can see that here, This is an edge. This is an edge. This is an edge. So I have 9 edges, all of them mutually non-adjacent. Okay. And they are adjacent to this common edge. So this is a property not of a graph, but it could be enjoyed by a semigraph. Okay. And another important thing of this semigraph is so many properties which could not be generalized to hypergraph, that can be generalized to the semigraph. Okay. For example, this is a hypergraph. Hypergraph is, instead of taking 2 vertices as an edge, okay, you can take any subset of the vertex set as an edge. So this is an hypergraph having 3 edges. Here you have this edge containing 4 vertices. This is an edge containing 3 vertices. And this is an edge containing 2 vertices. So hypergraph is one generalization of a graph. And this one is another generalization. And now can you see this screen, an introduction to semigraphs, that screen?
Yes, ma'am. Yes, ma'am. Your PDF is open now.
Okay. Is it visible, sir?
Yes, ma'am. It is visible. It is visible.
Okay. So this is the motivation. You are going to interpret an edge. In the usual graph, how do you draw an edge? You take 2 vertices. You put a line between those 2 vertices. That is an edge. Okay. So now you are going to concept it in a different way. Instead of looking at an edge as a diagram, you take it as a 2-element subset of the vertex set. Okay. So if I want to draw an edge, I need 2 vertices. So every edge can be taken as a 2-element subset of the vertex set. That is one way of interpreting an edge. Second way is you can treat an edge as a tuple, but it is an unordered tuple. Even though you write it as u comma v is same as v comma u. That is what you are writing here. So it is a 2 tuple u comma v, and u comma v and u dash comma v dash. The 2 tuples are equal if and only if the corresponding coordinates are equal. That is u equal to u dash and v equal to v dash, or u equal to v dash and v equal to u dash. So these are 2 ways in which you can interpret an edge. And hypergraph theory developed by Birch, that is a generalization of A. So their question is, instead of taking an edge as a 2-element subset, why not I take it as a 3-element subset or 4-element subset? That is the generalization of hypergraph. Okay. Semigraph developed by Professor Sampath Kumar, that is a generalization of the second approach. Why should I take a 2 tuple? Why not I take a 3 tuple or 4 tuple or 5 tuple, etc.? That is the way in which he generalized. Okay. So this is the definition. So it is a pair. You have a non-empty set of vertices. You have a non-empty set of edges. But now an edge is a n tuple. Okay. I can have any set of vertices, any number of vertices. So V is the same. V is a non-empty set whose elements I call as vertices. Okay. But X is, that is set of edges, is now a set of n tuples of vertices. And all the vertices should be distinct. I should not repeat the vertices. So it is the n tuple of distinct vertices. N can be anything greater than or equal to 2, satisfying 2 axioms. So semigraph axioms or semigraph axiom 1 and 2. Axiom 1 says that any 2 edges have at most 1 vertex in common. Okay. So all the vertices in the n tuple should be distinct. 2 edges can have at most 1 vertex in common. So either they don't have anything in common, or if at all they have a vertex in common, they cannot have more than 1. Okay, that is the first thing. And the second condition says that you can have the vertices in the reverse order also. That is u1, u2, etc., un, and v1, v2, etc., vm. They are 2 edges now. First one is an n tuple. Second one is an m tuple. And they are equal means n should be equal to m, and either correspondingly u1 equal to v1, u2 equal to v2, etc., or in the reverse direction. u1 is equal to vn and so on. Okay, that is what I have written here. So the edge u1, u2, etc., un is the same as the edge un minus 1, etc., u1. Because it is an unordered pair, an edge is an unordered pair. We don't consider digraph. Okay, it is a usual graph. So that unordered pair is generalized here. So that is u1, u2, etc., un, and that is same as un, etc., this. When you look at the diagram, things will be clear. Okay. So let me introduce the terminologies. Take one edge. So an edge is now an n tuple. V1, V2, etc., Vn, that is an edge. So the V vertex V1, that is the starting vertex, the first vertex, and the nth coordinate, that is Vn, they are called as end vertices. So V1 and Vn are called as end vertices. And all the others are called as middle vertices, except the first and the last. The others are called as middle vertices. Okay. So if a vertex is only end vertex, it is an end vertex of every edge, means it is called as an end vertex. If it is a middle vertex alone, it is called as a middle vertex. But when you look at the example, you can see that middle vertex of one edge can be an end vertex of another edge. In that case, it is called as a middle cum end vertex. Okay. So you have three type of vertices: end vertex, middle vertex, middle cum end vertex. Okay. So let us see one example. You take any graph. Okay. From that graph, you take H to be the collection of all the paths having at most one vertex in common. Okay. Sorry. So you take this. Here it is an usual graph. You think of it as an usual graph. So this is taken now as one edge in my semi-graph. Okay. So this is one edge. So that is a path. This is a path in my graph. In my semi-graph, it is an edge. So this is one edge. This is one edge. This is one edge in a semi-graph. So all the paths having at most one vertex in common, if that is taken as the edge set, then this is a semi-graph. So this example is a semi-graph with seven edges. Okay. I have these 6 paths together with the base path, 7 edges, and that is a semi-graph. Okay. So look at this diagram carefully. So you can very well understand what I mean by a semi-graph. So this is the pictorial representation of a semi-graph. I have 7 vertices, 1, 2, 3, 4, 5, 6, and 7. So the number of vertices in the semi-graph is 7. Okay. And what are all the edges? See, this is an edge. 1, 2, 3. That is an edge. That is the tuple. The 3 tuple, 1, 2, 3. That is an edge. So you can see a difference here. Some things are represented by bold vertices. Some are represented by circles. Okay. And as you can remember, there are 3 types of vertices: end vertices, middle vertices, and middle cum end vertex. Okay. So end vertices are denoted by bold dots. That is this one. 1 is an end vertex. Okay. 3 is an end vertex. Middle vertices are represented by circles. So 2 is a middle vertex. Okay. So what I have here, this 1 is an end vertex, 2 is a middle vertex, and 3 is an end vertex. Okay. Can you see the screen, sir?
Yes, ma'am.
ma'am.
We can see.
Okay. So this is an edge. 1, 2, 3 is an edge. So 1 is an end vertex, 3 is an end vertex, 2 is a middle vertex. This is one edge. And coming to 3, 6, that is that single edge. That is the 2 tuple. So that is an edge. And coming to this one, 5, 6, that is again a 2 tuple, that is an edge. And then 3, 7, 5, that is an edge. 3 is an end vertex, 7 is the middle vertex, 5 is an end vertex. Okay. And here you could see small tangents here, because this tangent represents this vertex 7, which is the middle vertex of this edge 3, 7, 5. That is also an end vertex of 1, 7. Okay. So in my semi-graph, 1, 7 is an edge. So this vertex 7, it is not alone a middle vertex. It is also an end vertex. So it is a middle come end vertex. So middle come end vertices are represented by a small circle together with small tangents. So this is the representation of a semi-graph. So how many edges does this semi-graph have? 1, 2, 3. That is a 3 tuple, which is an edge. 1, 7. Okay, that is one edge. 7, 6. That is one edge. 3, 6 is one edge. 5, 6. That is another edge. So I have 5 edges in the semi-graph. Okay. So any representation for a semi-graph will have dots, that is bold dots, circles, and then these tangents. These informations gives whether they are middle vertices or end vertices or middle come end vertex. Okay. So an edge is now a Jordan curve. Normally I put them as a straight line, but if depending on the position, I can use a curve also. Okay. So the middle vertices represented by small circles. End vertices which are not middle vertices are represented by thick dots, and a middle end vertex, okay, that is represented by small tangents. And suppose if I have a middle vertex, which is a middle vertex of some T edges, E1, E2, etc., ET, then the diagram would be a little bit cumbersome. That is, you have so many tangents, you have T tangents, so it may not be looking neat. So what you follow as convention is, you represent that circle by a small regular polygon with 2 T corners. Okay. And let me give an example for that. See here, this is a semi-graph with 4 edges having a common middle vertex. So this is a middle vertex. So this middle vertex is represented by a polygon with 8 vertices, 8 corners. So the number of edges is 4. So all of them having this particular vertex as a middle vertex. So instead of representing it by a circle, okay, I represent it by a polygon with 8 corners, with the assumption that the edge E1, if it crosses or meets this middle vertex at C1, and also it meets it at C5, that is C1, C5. 5 is this, okay, you take it as T plus I minus this, that is this one. Ci and Ct plus I, that is how you look at it. So the edge E1, it crosses through C1 and C5. The edge E2 crosses through C2 and C6. The edge E3 crosses through C3, C7. Edge E4 crosses through C4 and C8. Okay. So this is just a representation. And this you can see it is an application of semi-graph. You can take a very big family, a family having some 4 or 5 generations, and the relationship among all the members of the family can be represented by a semi-graph. So what I have in this diagram is, this is one edge, A, C, D, B, that is one edge. C, L, E is another edge. D, M, F, that is one edge. L, K, that is one edge. G, K, I, H, that is another edge. So what are all the informations I have is, all the end vertices are parents and the middle vertices are children. So A and B parents, their children are C and D, that is the first edge. And C, again it is an end vertex because here I have a tangent. So C and E, they are parents of L. So L is the child. Okay. Similarly, D and F, they are parents of M. But M is unmarried. Okay, so M is there. And but this L, he has again married to K. So L and K, they are waiting for a baby you can take. So L and K, they are again married. So you have an edge. And K, the parents of K are G and H. So G and H are the parents of K. And K has some unmarried brother or sister, I. Okay. So the entire information can be represented by this semigraph. And you can represent their sex, whether they are male or female, either by a plus or minus sign. And also the age can be represented by putting weights to the vertices. Okay, suppose if the age of A is 80, I can put a label 80 here. Okay. So the entire relationship can be represented in the semigraph. And this is another example of a semigraph called as straight edge semigraph. What you do is you take the Euclidean plane, draw so many straight lines, okay, so many straight lines in the Euclidean plane, and you can see that, you know that any two straight lines, if at all they intersect, they can intersect only at one vertex, okay. So you, in each of these straight lines, you take vertices, minimum 2 vertices. So I have drawn 6 straight lines, okay, and I have taken vertices. So if I take this particular straight line, I have taken 4 vertices in that particular straight line. So that is B. B is the collection of distinct points I have taken. And this is one edge in my semigraph. Okay. One straight line with these 4 vertices, that is one edge. Okay, this is another edge. So each edge in the Euclidean plane becomes an edge of the semigraph. So this is one natural example. It is called as straight edge semigraph. And then you have Steiner's triple system. That is, you take a set with n points. Okay. You take 3-element subsets. Okay, the set of 3-element subsets of X with the condition that if I take any 2-element subset, that is a subset of exactly one triple. Okay. So for example, if you take a Steiner triple system of order 3 means, so you have only 3 vertices. So there is only one 3-element subset, 1, 2, 3. Suppose if I take Steiner triple system of order 7, so I have 1 to 7. So you can take all possible 3-element subsets, but with the condition that one 2-element subset can be a subset of only one triple. So if I take 1, 2, 3, I cannot take 1, 2, 4 because 1, 2 will be subsets of both of them. Okay. So carefully you have to choose this. And here you can see that it is a semigraph because of this condition. Each 2-point subset is a subset of exactly one triple. So if at all they intersect, they can intersect in only one vertex. So that is the first axiom of a semigraph. Okay. So this every Steiner triple system is a semigraph. So the beauty of the semigraph is you can have so many situations, okay, which are turned to be semigraphs. So this is an ordered partition semigraph. So ordered partition of a positive integer n means you take a partition of n, that is a k tuple n1, n2, etc. nk. When I add n1, n2, etc. nk, I should get n. So sigma ni should be equal to n. Okay. So that is a partition of n. So an ordered partition semigraph that is denoted by G n comma r. V is the set of elements 1, 2, etc. n. That is the first index here. N is the first index. So my vertex set is 1, 2, etc. n. And what is X means? X is the set E, which is a partition of the elements of V, should contain, the sum should be equal to this particular n. Okay. And this R is, R elements should be there. So the R can be 2, or can be 3, or can be 4, whatever it is. So I take representations from this V. The number is R. Okay, I should take R elements, and that sum should be equal to this n. If you look at this example here, see, this is G7, 10. So 7 is n. So I have 1, 2, 3, 4, 5, 6, and 7. I can use only them. And this 10 is the number I need. Okay. So from these 7 elements, that is 1, 2, etc. 7, I have to find out the partitions of 10. Should be only from this 1 to 7. Okay. So you take 1, 2, 3, 4. 3 is represented as a polygon here. 3 is represented as a polygon with 4 sides. Okay. So I want 10. So what I take is 1, 2, 7. You can see that it sums up to 10. So 1, 2, 7. So 1 is an end vertex. 7 is an end vertex. 2 is a middle vertex. Okay. So this is one edge. 1, 2, 7 is one edge. Okay. And see, this is a polygon. Okay. So if I come here means I go out from this. So this is 1, 3, 6. That is one edge. So 1, 3, 6. That is another partition of 10. Okay. And then 5. I come here. So I go here and then come out. So 5, 3, 2. So 5, 3, 2. That is another partition. So 2 has now become an end vertex of the edge 5, 3, 2. So here I have a tangent. Okay. So 2 is the middle vertex of this edge, and it is also an end vertex of another edge. And coming to this 7 with 3. So it total comes up to 10. So this 3 itself has become an end vertex. So the vertex 3 is represented by this polygon. So that 3 itself has become an end vertex. So that is represented by this tangent. Okay. So hope you can follow. So there are only 3 things. Bold dots, end vertices. Middle vertices represented by circles. And middle come end vertex represented by circles with tangents. That's all. Okay. So this 3, it is a middle vertex of this edge 1, 3, 6. It is also a middle vertex of the edge 5, 3, 2. But it is an end vertex of the edge 7, 3. So here I have a tangent. Okay. See, this is G6, 12. So 6, I have 1 to 6. So I should find all the partitions of 12 using 1, 2, 3, 4, 5, 6. Okay. So that, of course, nothing should be, not more than 2 should be repeated. Okay, only 1 can be repeated. So I have 6, 2, 4. That is one partition. 6 is an end vertex. 4 is an end vertex. 2 is a middle vertex. Okay. So that is one edge. And coming to this, 6 is an end vertex. 5 is an end vertex. 1 is a middle vertex. So that is an edge. And then 4, 3, 5. That is an edge with 3 as a middle vertex and 4 and 5 as end vertices. Okay. See, the beauty of the semi-graph is, it is new. Okay, it is constructed only now. So each and every concept in graph theory, what are all the things you have studied in graph theory, you can get it here. You can generalize or define it here, and you can do work on this. Okay. So many things are open. Everything is open. Okay. And another interesting thing is, each and every definition can be generalized in many different ways. For example, if you look at degree, I'll be defining degree in a degree of a vertex. You can see that I can define degree in 5 ways. And all of them coincide in the case of an ordinary graph. That is the beauty of the semi-graph. Okay. So the first definition is semi-graph isomorphism. When do you say that 2 semi-graphs are isomorphic? It is as in the case of a graph, I should have a bijection between the vertices, okay, such that whenever V1, V2, etc., Vn is an edge in G, the corresponding images f of V1, f of V2, etc., f of Vn, that tuple should be an edge in G dash. Okay, that is the natural way of defining isomorphism. And other type of isomorphisms are also defined. And now you can define a sub-edge. So sub-edge is a part of an edge. That is, if V1, V2, etc., Vn is one edge. Sub-edge means I can leave off some vertices in this edge. I can take some, but I should not change the order. Okay, because here I know that it is V1 will occur first in my edge. So V1, V2, etc., Vn. So if I take V1, I can leave off V2. That is allowed. I can leave off vertices. So I can take Vi1, Vi2, etc., Vik. But the ordering should be preserved. I cannot change the order. So in the n tuple, you can leave off some things. And without changing the order, you can write some vertices. That is a sub-edge. And the third one is, and it is said that E dash is induced by, you just write the vertices alone. And the next one is partial edge means, you can, if you take one vertex, you have to take it consecutively. In between, you cannot remove. Okay. So it is a j minus I plus 1 tuple. It is represented like this. It is a partial edge. So it is not subset, or it is simply not a subset. It is a part of that. Or you make a cut at Vi and Vj and you take that middle part. So it is E of Vi comma Vj. Means I start from Vi. I should not leave anything in between. If I take Vi, I should take Vi plus 1, Vi plus 2, etc. up to Vj. So that part entirely should be taken. That is a partial edge. So any two consecutive vertices in E dash, they are also consecutive vertices of E. Okay, so that is called as partial edge. So you have two types here, sub-edge as well as partial edge. Okay. And if I take any edge, means the usual edge, it is also a sub-edge of itself, and definitely it is also a partial edge of itself. Okay. If I take a proper sub-edge or a proper partial edge, it cannot be an edge. Can you understand? Because if it is an edge, the original edge and this sub-edge, that will have more than one vertex in common. So that cannot happen. So here a sub-edge and a partial edge will not be edges, may not be edges. Okay. So and then you define so many type of semigraphs. Sub-semigraph. Okay. That is the usual way. V dash is a subset of V and G dash are sub-edges. So if you take the original edges as X dash, and for every edge, if you take sub-edges are what you defined now. Okay. That is called as sub-semigraph. And then induced sub-semigraph means the edges or sub-edges of G induced by all the vertices in V dash. Okay. And then just like sub-semigraph, you have partial semigraph. So the difference is, instead of taking sub-edges, you take partial edges. Okay. And then when do you say that sub-semigraph is a spanning sub-semigraph? If the G dash contains all the vertices of G. Okay. And an edge is called as a FS edge, means either it is an edge or a sub-edge. And FP edge means edge or partial edge. And two sub-edges or disjoint means their intersection is less than or equal to 1. Okay. And then you walk. So as you have in the case of a graph, it is an alternating sequence of vertices. Okay. It's an alternating sequence of vertices and edges. Edges means you can have either sub-edges or partial edges. So here you have sub-edges, FS edges. So vertex for a sub-edge, vertex, sub-edge and so on. So that is V0, E1, V1, etc. Beginning and ending with vertices. And the condition is this E1 will be an n tuple, some n tuple. It should have end vertices as V0 and V1. Okay. And all the vertices of this E1 is a sub-edge, all the vertices in that E1 should be taken into account. Okay. So EI, the end vertices of EI or VI minus 1 and VI. Okay. So they are the end vertices of this FSH EI. So it is called as a V0 Vn walk. And as we have in the case of a graph, if V0 equal to Vn, it is called as a closed walk, otherwise it is open. Okay. So a V0 Vn walk, it contains all those vertices in that FS edge EI. No vertex can be left out. So instead of writing that EI, you can also write the vertices that you have taken in EI. Okay. And then you come to the second stage, that is definition of a trail. So all the edges should be disjoint. So if all the edges are disjoint, the walk is called as a trail. And then the trail becomes a path if in addition the vertices are also distinct. Okay. Cycle is a closed path. So in a similar way, you can define another path is an S path. That is a strong path means if these FS edges are also FP edges. That is, they are partial edges. Partial edges means if you start from a vertex, you cannot leave any vertex. Consecutively, you have to take all the vertices and then you can stop at a vertex. Okay. They are FP edges, partial edges. So if all the edges are partial edges in a path, it is called as a strong path or S path. Otherwise, it is called as a weak path. Similarly, you have an S cycle and a weak cycle. So this is an example. If you take this semi-graph, I have given you a walk, that is V0, V1, V2. Okay. So I take this V0, V1, V2, that is one edge, and then I come back here because it is all partial edges, V2, and then V2, then V1. Okay. Then I take V4. So V1, this is a partial edge, V4, V5, then V6 and V7. So instead of looking at like this, if you look at together with the edges, that would be clear. Okay. But if you simply write the vertices alone, then there is no uniqueness because if I take the edges in a different way, you get two different walks. So you need not follow this terminology, you just write the edges. So if you look at this path, this is a walk. So start with V0 and the edge E1. E1 should be an edge having end vertices V0 and V1. So it is this ordered pair, V0, V1. Okay, so that is E1. And then E2 should have V1 and V2 as end vertices. So this is E2, V1, V2, that is end vertex. E3 should have V2 and V1 as end vertices. So E3 should be this edge, V2 and V1. Okay, that is E3. And E4 should have V1 and V4 as end vertices. So it is the edge V1 and V4 should be the end vertex. So it is V1, V4. Because it is a sub edge, I need not have V3. Okay, I can leave off this V3. So it is V1, V4 and so on. So you can write like this. See, this same thing can also be represented in this way. Because instead of taking V0 and V1, I can take V0, V1 and V2. That is a part of this edge. Okay, that is also there. So I can replace this E1 by this E1. So there is no uniqueness. If I simply write like this, there is no uniqueness. Better to have this terminology so that you have uniqueness. Okay. So if I write this trail, this is a trail because no edge is repeated. Okay, and also it is a path because no vertex is also repeated. But here the paths are not partial edges. The edges are not partial edges, so it is not a strong path. Okay. And these are graphs associated with a semi-graph. What are all the different graphs you can associate with a semi-graph? Okay. Here I have given you 3 different graphs, which graphs means the usual graph. They are not semi-graphs. Okay. So given a semi-graph, how many graphs you can associate with that semi-graph? That is the definition you are going to give now. Here you are going to associate 3 different graphs. Vertex set is the same. Okay, same as that of the semi-graph. How do you define the edges? Okay, So the first one is end vertex graph, GE. So two vertices in GE will be adjacent if and only if they are end vertices of an edge in G. So that is the first definition. So end vertex graph. So two vertices are adjacent if and only if they are end vertices of an edge. Okay. Let us go to the example first. So this is a semi-graph. I want to associate a graph with this. So that is the GE graph. See, if it is a blackboard means I could have both of them side by side. But here no other way. I have to go to the next slide. I couldn't fit in the same slide. So here you can see that 1 and 3. By my notation of a semi-graph, 1 is an end vertex, 3 is an end vertex, 2 is a middle vertex. Okay. So 1 and 3 are end vertices. So in my graph, 1 and 3 will be adjacent. 3 and 9 are end vertices. So 3 and 9 will be adjacent. 4 and 5 are end vertices. So 4 and 5 will be adjacent. 3 and 6 are end vertices. So 3 and 6 will be adjacent. Okay. So you just look at that graph. So 4 and 5 are adjacent. 3 and 6 are adjacent. Okay. So 2, you can see that 2 is not an end vertex. So 2 is not adjacent to anything. Okay. So the end vertices alone will be adjacent. So that is the end vertex graph. That is GE. And second one is the adjacency graph GA. So two vertices will be adjacent if and only if they are adjacent in the semi-graph. Okay. And naturally, how do you generalize adjacency? In the usual graph, if two vertices are adjacent means there is an edge joining them. Okay. So all the vertices lying in an edge are all adjacent. For example, 1, 2, 3. They are all in the same edge. So all of them are adjacent. 4 and 5. They lie in the same edge. So they are all adjacent. 3, 5, 6. That is an edge. So 3, 5 and 6 are mutually adjacent. So 6, 7, 8, 9. They all lie in the same edge. So all of them are adjacent. So in my graph, 6, 7, 8, 9, all of them are mutually adjacent. So they form a K4 there. And coming to this 6, 5 and 3, they form a K3. Okay. If you look at that graph, you can see that. So this forms a K4 and 3, 6, 5, they are adjacent. So that forms a K3. Coming to 9 and 5, you can see that 9 is here and 5 is here. So they are not adjacent. The edge containing 5 is, this is one edge containing 5. This is another edge containing 5. And this is the edge containing 9. Okay. So 9 and 5, they do not lie in the same edge. So they are not adjacent. So that is the adjacency semi-graph. And this is consecutive adjacency. That is, it is a part of GA. So no, adjacency alone is not sufficient. It should be consecutively adjacent. Consecutively adjacent means 6 and 7, they are consecutively adjacent. They lie in the same edge. Also, they lie consecutively. Coming to 6 and 8, they are adjacent, but not consecutively adjacent because they are not consecutive. So 6 and 7 will be adjacent in my graph, but 6 and 8 will not be adjacent. If you look at here, okay, you can see that 6 and 8 will not be adjacent, whereas 6 and 7 adjacent. So it is a part of or a subgraph of the adjacency graph, but you will not picture out all the adjacency. You picture out only the consecutive adjacency. Okay, that is GCA.
Okay, sir. Okay, sir.
And then you come to degree. So for any vertex V in a semi-graph, here you are going to define 5 type of degrees. Okay. And you can, the interesting thing is, if you go to a graph, all of them are the same. There is no difference at all. Because whenever you generalize something, when you come to the base part, nothing should be contradicted. Okay. So all these degrees, they coincide with the usual degree when you come to a graph. Okay. So the first one is simply degree. Okay, degree of V with nothing else. It is simply the number of edges having V as an end vertex. Okay, that is one way of looking at a degree. So it is the number of edges having V as an end vertex, that is degree. I think it would be easy if I give the example along with the definition. So this is the first way of defining degree of V, number of edges having V as an end vertex. So you look at this graph, come to 1. So what is the degree of 1? What I should look at? I should look at the number of edges having 1 as an end vertex. Okay, you can see that 1 is an end vertex of one. This is 3. So this 1 is an end vertex of only one edge. So its degree is 1. Coming to this vertex, it is a middle vertex. Okay, it is represented by a circle. So it is a middle vertex. And there is no tangent. Here there is no tangent. So it is not an end vertex. So it is not an end vertex of any edge. So its degree is 0. Okay. Coming to this vertex, it is a dot. So it is an end vertex of this edge. It is an end vertex of this edge also. And it is an end vertex of this edge also. Okay. So this vertex is an end vertex of 3 edges. So the degree is 3. Coming to this, it is an end vertex of this edge. It is also an end vertex of this edge. So its degree is 2. This one, middle vertex, not an end vertex. So degree is 0. And this one, it is an end vertex of 2 edges. It is an end vertex of this edge. It is an end vertex of this edge. So the degree is 2. Coming to this, end vertex of this edge alone. So 1. And coming to this vertex, even though it is a middle vertex, here you have a tangent. So this is one edge. Okay, so this is one edge. So this middle vertex is also an end vertex of this edge. So its degree is 1. So this is usual degree. Okay. And then you have similarly, you have edge degree. Edge degree is the number of edges containing V. Okay. So you can have the same example. Number of edges containing that vertex. See, if I take this, okay, this vertex, it is in only one edge, so 1. This vertex, it is in only one edge, so 1. Coming to this, it lies in 3 edges, so 3. This vertex lies in 2 edges, 2. So this is 1. This lies in 2 edges. This lies in 2 edges, so 2. This lies in 1 edge, so it is 1. That is edge degree. Number of edges containing that vertex. And then adjacent degree, that is denoted by degree of VA. Okay. That is the number of vertices adjacent to V. The number of vertices adjacent means lying in the same line. Number of vertices lying in the same edge. Okay, that is adjacent degree. If you look at this edge, see here you have 2 vertices. Okay. Number of vertices adjacent to that. This edge contains, totally it contains 3 vertices. So the number of vertices adjacent to this vertex is this one and this one. So the degree is 2. Same thing for this. Number of vertices adjacent to this vertex is this one and this one. So I have 2. Coming to this, the number of vertices adjacent to that is this alone. So it is 1. And for this, the number of vertices adjacent to this one is this one, and this one. So it is 3. And for this 5, the number of vertices adjacent to that is 1, 2, this one 3, this one 4, and this one 5. So for here you get 5. For this vertex, the number of vertices adjacent is 1, 2, 3. Okay. And for this one and this one. And for this one, and this 3. So that is adjacent degree. And then consecutive adjacent degree. That is the same. That is, you don't look at all the adjacency. You take only those vertices which are consecutive adjacent. Okay, that is similar to that. And then finally, ME degree. That is, it's an ordered pair, M comma E, where M is the number of edges containing V as a middle vertex. Okay, containing that vertex as a middle vertex. And the E is the number of edges containing that vertex as an end vertex. Okay, that is ME degree. So it is, for this vertex means number of vertices having that vertex as a middle vertex. No, there is no edge at all having this as a middle vertex. So it is 0. Number of edges having this as an end vertex, 1. Okay. If you look at this, number of edges having this vertex as a middle vertex. This alone is the only edge having this as a middle vertex. So it is 1. Number of edges having this as an end vertex. This one. So again 1. Okay. So once you understand clearly the representation of a semi-graph, things will be clear. So these are 5 types of degrees associated with semi-graphs. And you can see that always this relation holds. The degree of V less than or equal to this edge degree, less than or equal to consecutive adjacency degree, less than or equal to adjacency degree. And if you remember the first theorem in graph theory, it is itself called as the first theorem in graph theory. It says that sum of degree of all the vertices equals twice the number of edges. Okay. Similarly, you have a first theorem in semi-graph. You have these 3 relations. That is, sigma degree of Vi is 2 cube, and sigma degree of degree E, that is edge degree. Okay. Edge degree of Vi is cardinality of all the edges, sum of cardinality of all the edges. And this summation is this one, sigma I from 1 to cube, cardinality of EI square. So the proof is not not difficult. You can very easily follow. So I would skip the proof. Okay. And then now again you can define independency. So how many ways you can everything, each and every concept. Okay, each and every concept you can have so many ways to generalize. You have so many ways to generalize. That is the beauty of the semi-graph. Even for that degree, you define 5 types of degrees. Okay, but when you look at it as a graph, all of them are one and the same, because the degree of a vertex is the number of vertices or number of vertices to which it is adjacent, or the number of edges for which it is an end vertex. That is, both of them are the same. Okay. So all the generalizations coincide. So each and every concept can be generalized in many different ways. That is the beauty of the semi-graph. Okay. So this first one is simply independent, the usual way. So no 2 of them should be adjacent. So I take a set of vertices. No edge is a subset of S. Okay. Because adjacent means I should have all those vertices in a edge. All those vertices should be in that tuple. So that is an edge. So an edge should not be a subset of S. Okay. So a subset of S will never be adjacent. So that is the natural way. So that is independent. And E independent. S is E independent. No 2 end vertices of an edge belong to S. Okay. If 2 vertices are end vertices of an edge, they should not belong to S. That is E independent. Okay. And then strongly independent means no 2 adjacent vertices belong to S, because you can have so many adjacent vertices. No 2 adjacent vertices belong to S. That is called as strongly independent. So if you look at a graph, all of them are the same. Okay. And whenever you have the concept of independency, you can define a bipartite graph. Okay. So using this itself, I can define 4 types of bipartite graphs. Because in the normal sense, bipartite graph is a partition of the vertex set into independent sets. And here I have different types of independency. So for every type of independency, I have a corresponding bipartite graph. Okay. So the simply bipartite means the vertex set can be partitioned into two sets, V1 and V2, where they are independent. As in the first case, that is no edge is a subset of S. And if V1 and V2 are E independent means that is a E bipartite semigraph. Okay. And then if they are strongly independent means I have a strongly bipartite semigraph. Okay. And then I have edge bipartite semigraph means the traditional way in which I have it in the graph. You know that in the usual graph, a graph is bipartite if and only if it has no odd cycles. So if that is the definition, it is called as a edge bipartite semigraph. Okay. So the book that I am going to give here as the reference, it is actually a compilation work of Professor Sampath Kumar. Many people have generalized so many concepts. Coloring has been generalized to semigraph. Domination has been defined. But lot of things remain open. Okay. Whatever you study in graph, you can carry on to this semigraph. Okay, so this is the only semigraphs which are strongly bipartite or bipartite graphs. Okay. So this is the reference. It is a book, a collection of papers, compilation of papers edited by Professor Sampath Kumar, semigraphs and their applications. Okay. Our university library, it has a copy of 2 copies of this book. And I think St. Mary's College also, they have purchased copies of this book. This book contains almost all the things that are generalized to semigraph so far done. So it is a compilation work of Professor Sampath Kumar. And coming to the southern part of Tamil Nadu, Dr. Gayatri from Tyagaraja College and Professor Swaminathan from Madurai, both of them have done good work in semigraph. Okay. Yes.
Ma'am, once again your screen is not visible, ma'am.
Now I have not presented, sir.
Okay. Thank you.
Okay. So now it is for questions. Okay, now the time is for questions. Hope you had, because teaching mathematics in the online mode, that is that to introducing a new concept, it is not that easy. I hope you have a basic idea of what a semigraph is. Okay. So that is what I want, because you can go through the book and you can very easily understand what are all the things he has defined. But the very peculiar thing is, I want to promote this semigraph in the southern part because it has so much of openings. All the things that you have done in graph theory, okay, that can be carried over to semigraph. And there are various ways in which you can carry over to semigraph. That is another beauty of the semigraph. So it has very good scope for further research. So now the time is open for questions.
So dear
participants, if you have any questions, you can post them now.
Do I have questions in the chat box?
yes, ma'am. In YouTube, one of the person asked, ma'am, could you tell the real world applications of these semigraphs?
I think I gave one. The entire family relationship can be represented as a semigraph.
Yes, ma'am. They have asked in science.
In science, okay.
Any computer based or anything.
Oh, the computer network that can be represented. The entire network diagram can be represented as a semigraph. Because anything what you have in the usual graph can be represented as a semigraph. Okay. Actually, the book has a lot of applications.
Thank you, ma'am.
Maybe networking. Networking can be represented, the connection, network connections that can be represented as a semigraph.
Okay, ma'am. Thank you, ma'am.
Okay.
Dear participants, you can raise your questions by unmute yourself.
Matching as well as coloring and the extension anything.
பண்ணிட்டாங்க சார், பண்ணிருக்காங்க. அந்த புக்லயே ஒரு சாப்டர் இருக்கு சார். அந்த ஒரு எட்ஜ்னு பாக்குறீங்க இல்லையா, it is an n tuple. So no vertex in that n tuple should be given the same color.
Oh, okay. Madam, is there any research work going on here?
Yeah, a lot of people. Gayatri madam, she has produced some 4 theses in semigraphs.
Oh, yes.
நமக்கு southern partல ரொம்ப வரல சார்.
Familiar இல்ல.
மதுரையில நிறைய பேர் work பண்றாங்க. In Madurai, some 2-3 people are working on semigraphs.
Okay, madam.
And in Mysore and Delhi also people are working. The entire book is on semigraph. Professor Sampath Kumar, he has published a book containing some 18 papers on semigraphs.
Okay.
People from Delhi are working, sir. Students of Dr. Acharya, Purnima Gupta and others. Regarding that book, I will send you the email ID of Professor Sampath Kumar. If you give him an email, immediately he will send you the book. You can just pay after the getting the book.
Okay.
I would send it to you, sir. My presentation also, I will send a copy to you. I will share with you.
Okay.
And also the email ID of Professor Sampath Kumar, that also I will give it to you, sir.
Okay, madam. Thank you.
Because one of the participants, she has asked whether the book is easily available. Once you send a mail to him, immediately he will respond and he will send the book to you. It is actually a publication of ADMA, sir. ADMA, there is an Academy for Discrete Mathematics in Mysore. And the ADMA word a publication in the book.
Okay.
St. Mary's College, I think they have bought 2 books.
I see. Yeah.
Recently, Punita madam, she suggested me whether to have any new books, and then I gave this as a suggestion. It is very cheap only, some 350 or something.
Yes. A nice introduction, madam.
Thank you, sir.
Ma'am, one question from YouTube chat box. The Professor Vimala Shanmugavel asked the question. Ma'am, could you, there is any relation between semigraphs and geometrical spaces?
Geometrical spaces, I don't have any idea. What do you mean by a geometrical space then? She cannot talk here, no?
No, ma'am. They are watching through YouTube.
I don't have any idea about geometrical space. What do you mean by geometrical space? Actually, what I gave an example, that is the straight line drawn in Euclidean space.
Yes, ma'am. That's why she has asked this question. I think so.
Each straight line can be taken as a semigraph. That is what I meant there. But I don't have any much of idea about a geometrical space, sir.
Dear participants, if you have any other questions, you can ask through chat box or by unmuting yourself. Those persons who are watching through YouTube, you can put your questions in the YouTube chat box.
And Nagarajan sir, I'll send my presentation to your mail. And also the email ID of Professor Sampath Kumar also I'll send to you as mail.
Okay, madam. Thank you, madam.
You can share with the party.
Okay, madam.
மேம் எனக்கு ஒரு டவுட். நீங்க இந்த செமிகிராஃப்ல வந்து டிகிரி வந்து டிஃபைன் பண்ணும்போது 5 டைப்ஸ் சொன்னீங்கல்ல மேம்?
ஆமா.
there are 5 types in 5 ways we can define அந்த டிகிரி வந்து டிஃபைன் பண்ணல மேம். அப்படி டிஃபைன் பண்ணும்போது ஃபர்ஸ்ட் அந்த டிகிரி விலயே வந்து நம்ம வேரியஸ் வேஸ்ல வந்து நம்ம டிகிரி வந்து டிஃபைன் பண்ண முடியுமா மேம்? யூசுவல் டிகிரி வந்து யூனிக்கா இருக்குமா?
யூசுவல் கிராஃப்லயா?
இல்ல செமி கிராஃப்ல மேம்.
செமி கிராஃப்ல டிகிரி வி இல்லையா?
டிகிரி வி.
டிகிரி வினா நம்பர் ஆஃப் எட்ஜஸ் இன் which is an end vertex அப்படிதானே?
எஸ் மேம்.
அதுக்கு வந்து அது மட்டும் தான் டெஃபினிஷன்.
இல்ல எட்ஜ் நம்ம வேரி பண்ண முடியாதா மேம் இங்க?
எட்ஜ்யா? எத்தனை எட்ஜுக்கு அது end vertex-ஆ இருக்கும்? அது எல்லாமே சேர்த்து தானே எழுதுறோம். என்ன மீன் பண்றீங்க நீங்க?
இல்ல எனக்கு அந்த டிகிரி கம் n வெர்டெக்ஸ்னு ஒரு வெர்டெக்ஸ் இருக்குல்ல மேம், அங்க வந்து டிகிரி எப்பவுமே 0 தானே? மிடில் கம் n வெர்டெக்ஸ் அதுல வந்து டிகிரி எப்பவும் 0 தானே மேம்?
எண்ட் வெர்டெக்ஸ்க்கா?
இல்ல மிடில் கம் டிகிரி வந்து மிடில் கம் n வெர்டெக்ஸ்க்கு 0 தானே மேம் சொன்னீங்க?
அது வந்து சேஞ்ச் ஆகுமா இல்ல எப்பவுமே அப்படிதானா?
இல்ல மிடில் கம் எண்ட் வெர்டெக்ஸ்க்கு எண்ட் வெர்டெக்ஸாவும் இருக்கிறதுனால இட் வில் ஹேவ் a டிகிரி இல்ல. ஏன்னா இப்போ நம்ம டிஃபைன் பண்றது வந்து the number of edges having that vertex as an end vertex. சரியா? Okay. அப்ப if you take a middle come end vertex, then you suppose if it is an end vertex of 2 edges means its degree is 2. நம்ம டிஃபைன் பண்ணன அஞ்சும் தனித்தனியா யூனிக் தான்.
தனித்தனியா யூனிக்கா? அப்போ டாமினேஷன் நம்ம டிஃபைன் பண்ணா கூட அப்பர் பவுண்ட் வந்து டிகிரி வைக்கும்போது இந்த 5 வேஸ்லயே நமக்கு அப்பர் பவுண்ட்ஸ் வரும் இல்ல மேம்?
டாமினேஷன் நீங்க எப்படி டிஃபைன் பண்றீங்கங்கறத பொறுத்து இருக்கு. ஏன்னா யூசுவல் அட்ஜசன்சி தான் பண்றீங்களா, கான்சிக்யூட்டிவ் அட்ஜசன்சி பண்றீங்களா அப்படி நிறைய சான்சஸ் இருக்குல்ல.
சரி மேம். சரி.
The book contains one paper in domination.
ஓகே மேம்.
அது வந்து நாம எப்படினாலும் டிஃபைன் பண்ணிக்கலாம், எந்த டிகிரினாலும் எடுத்துக்கலாம்.
ஓகே மேம்.
நம்ம டிஃபைன் பண்ணன அஞ்சும் தனித்தனியா they are unique.
ஓகே மேம். Thank you மேம்.
Okay ma'am. But whenever you are going to generalize something, you should be careful that it doesn't contradict what already exists. அதனால generalize பண்ணும்போது ரொம்ப கேர்ஃபுல்லா இருக்கணும். அத வந்து கிராஃப்க்கு மாத்தும்போது, because every graph is a semi graph. You can take an edge as a 2 tuple, so it becomes a semi graph. அப்ப அப்படி பாக்கும்போது it should not contradict what that exists already in a semi graph. Okay. So you have to be very careful in generalizing.
Okay. Thank you.
Okay.
Ma'am, one more question from my side.
Yeah.
Can we extend it to the other part like fuzzy, soft or nano graphs? நம்ம பொதுவா கிராஃப்ஸ் எல்லாத்தையும் ஃபஸி கிராஃப்ஸா கன்வெர்ட் பண்ணாங்களா மேம்? அந்த தியரம்ஸ் எல்லாத்தையும் அதே மாதிரி இந்த செமி கிராஃப்ஸையும் நம்ம கன்வெர்ட் பண்ண முடியுமா மேம்?
அது தெரியல, அத பத்தி ஐடியா இல்ல. ஆனா மேபி தெரியல எனக்கு அத பத்தி. எனக்கு இந்த நானோ ஃபஸி பத்தி ஒரு ஐடியா இல்ல. ஓகே
மேம். பட் ஆனா இந்த ரியல் வேர்ல்ட் அப்ளிகேஷன்ஸ் அப்படிலாம் சொல்லும்போது நீங்க நெட்வொர்க்கிங் சொல்றீங்களா, அதனால ஐ திங்க் we can try. Can be definitely ma'am.
But whatever thing you have in graph can be done there. So appo naturally idayo, but you have to be careful. Adha onnu da idala main thing. Very careful in generalizing.
Sure ma'am. Okay. I think most of the persons have replied as very informative and crystal clear talk அப்படினு சொல்லிருக்காங்க மேம்.
Okay, thank
very
you.
Nice.
Was there any hindrances in between the voice modulation la idlayavadhu?
No ma'am.
Okay.
I think உங்க face மட்டும் தான் மேம். ப்ளீஸ் உங்களோட நீங்க கொஞ்சம் இன்ஃப்ரண்ட் வந்ததனால உங்களோட face மட்டும் தான் but now it's clearly visible ma'am. It was I think it was an extraordinary presentation, very informative too.
Thank you sir. Online la வந்து எவ்வளவு தூரத்துக்கு அது இதா இருக்கும்னு தெரியல, நேரா இருந்தா இன்னும் கொஞ்சம் நல்லா இருக்கும். Okay,
definitely ma'am. Safina ma'am, shall we proceed?
Yes sir. So thank you ma'am for taking us through the concepts of semigraphs, starting from the motivation, eventually taking us through giving us an idea about how to generalize basic graph theory concepts to semigraphs, and as a result you have given us a scope for research in semigraphs. Thanks a lot ma'am. And may I now call upon Dr. S. Jackson, Assistant Professor, PG and Research Department of Mathematics, B.O. Chidambaram College, to give the vote of thanks. Sir, please.
Thank you ma'am.
Thank you sir. Thank you.
So good afternoon everybody. It's a great privilege to propose a vote of thanks for this international faculty development program organized by our Department of Mathematics. First of all, I would like to place my sincere thanks to our Honorable Secretary Sir, Shri APCV Chokkalingam, for the pillar of support every event happening in our college. Next, I would like to sincerely thank our principal sir, Dr. C. Veerabahu, for his motivating and encouraging words whenever we approach him. So thank you, sir, for granting permission for this wonderful FDP and for his informative inaugural address. Thank you so much, sir. So a resource person is the key of the success for a particular for any event. For this event, we have gifted with such a person. So a good start is half done is a great proverb said. So I would like thank Dr. Kala ma'am, Professor and Head, Department of Mathematics, Manamnem Sundarna University, for accepting our invitation, and she gave a wonderful lecture and interesting one, which initiated a new research pathway in the southern part in the topic of semigraphs. Thank you so much, ma'am. I have attended so many workshops and national and international level workshop where you are the resource person. Whenever I attend a workshop, you have come up with a new idea. So I remember one thing. 2019, I have attended a workshop at Sadakutulappa College where you have taught us the polynomial graphs, the graph polynomials. Since I remind that topic, thank you, ma'am. Thanks for your informative talk. Thank you so much, ma'am.
Thank you, sir.
So without them, nothing would be happen in our department, and this is our department faculties. I thank each one of them for their active participation and support to conduct this international faculty development program. Thanks, dear faculties. And you can see this faculty development program through our official college YouTube channel, that is VOCC Watch. It's because of these persons. So Dr. John Prince Soundaranayagam sir, our ICA coordinator, Dr. Radhika, our ICA assistant coordinator, and Mr. Gomadi Nayagam, the technical expert, HOD, Department of Computer Science. I have to place my sincere thanks to them for their technical support. Thank you, dear professors and dear participants. You are serving the success to any event. So thank you. Thanks for participating. You have given with a good start. I hope we will have some good initiative, some breakthroughs throughout this faculty development program. So thank you all, dear participants. I thank each and everybody if I missed anybody in those days. Thank you.
So a professional vote of thanks, sir. Very nice.
Thank you, ma'am. Thank you.
Very nice. First time I have seen a vote of thanks with sharing, screen sharing. It's a good idea.
மேடம், எங்க இதுல சபினா தேவின்னு ஒரு மேடம் இருக்காங்கல்ல,
ஆமா,
சபினா தேவி அவங்க ஜாயின் பண்ணிருக்காங்க ரீசெண்டா. அவங்க ஐஐடில தான் பிஹெச்டி முடிச்சிருக்காங்க. கிராஃப் ரிலேட்டட், கம்ப்யூட்டர் ரிலேட்டட் கிராஃப் தியரியில முடிச்சிருக்காங்க.
ஓகே சார். ஓகே ஓகே.
இப்போ நியூவா ஜாயின் பண்ணிருக்காங்க.
ஓஹோ, சரிங்க சார். சரி சரி.
So
ஐஐடி எங்க சார்? ஐஐடி சொன்னயா?
IIT மெட்ராஸ்
மெட்ராஸ்.
PhD பண்ணலாம்.
சரி சரி. யாரு கைட் யாரு?
டாக்டர் சவுனகா மிஸ்ரா மேம்.
ஓகே ஓகே.
Thank you, ma'am. Very nice presentation. Thank you very much, ma'am.
Thank you, sir. Thank you. Thank you, sir.
dear participants, the feedback come attendance form have shared through the chat box. Kindly fill it to make sure your attendance in this webinar, in this faculty development program. Thank you. Thank you so much, ma'am.
Thank you, sir. Thank you. Okay, okay, sir.
Sure.
Thank you,
thank you.
ma'am.
Thank you.
Okay, okay. Thank you, sir. Thank you. Shall I leave, sir, then?
Definitely, ma'am.
Okay, ma'am. Okay.
Thank you, one and all. Kindly note the feedback link is shared in the chat box. Do fill it as soon as possible. It will not be available after half an hour. Jackson sir, right?
Yes, ma'am. Yes,
Half an
ma'am.
hour. Please do it within half an hour. Thank you.
So we have shared the link in both YouTube and Google Meet platforms. Dear participants, kindly fill it within half an hour. So after half an hour, it won't be working.
யூடியூப்ல உள்ளவங்களுக்கும் போயிருக்காது.
Yes, sir. Yes, sir.
ஓகே.